today, what we are going to talk about is how to make accurate map projections. Okay, the whole thing is that there are different types of maps, and we're not talking about. You'll see in a second. So basically, when you are looking at the globe, what are the different types of projections based on the way that you look at the map? Now, you have muted yourself, please. Okay, so guys, mute yourselves. All right, first of all, I'm going to go against what some of you actually believe, and the Earth has a curved surface. Okay, the Earth is actually round, it is not flat. Okay, the problem with it having a curved surface is it's very, very, very difficult to figure out true distances and directions on a flat map. So the way that you look at the map, or the way that the map was taken from this globe, basically, if you have your globe here, right, it's round. Well, we have to somehow figure out how we're taking this roundness and making it flat so that you can carry it around, or you're not exactly carrying your globe around everywhere you go, right? So when you're looking at map projections, it will actually happen a little bit easier once you see it, okay? So this is the first map projection. It's called a Mercator projection, okay? It's the typical one that you see in social studies class, or you've seen since you were little. It's when they take the globe and then they basically take a piece of paper around the globe, right? And then they unpeel it. Okay, this is my schedule. There's nothing really unusual about it. But when you unpeel it, you actually distort what you're looking at. So it goes from being a true size to now being on a flat map. It gets completely distorted. And something you want to notice in this map up here, excuse me, Greenland looks like it's the same size as North America, and it's really not. Right? So what is a Mercator projection? It basically shows the world as one continuous map. Now, this has led to flat earthers believing that they are true, that they are correct, I should say. The earth is not flat, and I'm going to prove it to you either today or tomorrow, that the earth is not flat. All right? So in this case, true distances are straight lines, which is very difficult to figure out because we know that at some points you go uphill and downhill. Even if you drive from New York to Pennsylvania or New York to Florida, you know that you're not going in a straight line the whole time, even though you might be hugging the coast, right? There are going to be turns that you have to go. You're going to be tunnels that you go through. Sometimes you go up a mountain to come back down the mountain. It's just the way that the road is built, right? Okay, so like I said, the problem is with this map is that the higher that you are in latitude, and remember the latitude lines are the horizontal ones, the ones that go from left to right, but they move up and then down, right? Because in this checkerboard, you can see that we have the longitude lines, the long lines, and the latitude lines that kind of looks like a letter, the rungs on a letter. That's how you're going to remember it. Okay, the higher up in altitude you go, when they peeled off that piece of paper, it made it look like those countries at top are much bigger than they actually are. It's just the perception. So like I said, Greenland is only 1/12 the size that it's being shown in this picture. Okay, it's not as big as North America. All right. The second type is a mnemonic projection. Now, a mnemonic projection is when you take your globe and you look at it from up above. So it's literally, if you're looking here, if you're just standing over it, what do you see? Okay. Couple things to notice, right? This is what North America looks like. Guys, turn off your mics, please. Okay, I can hear you. Okay. But here's North America in a mnemonic projection. So if you look at it, and this is supposed to be Mexico here. Okay. If you're looking at it, you can see that North America is very elongated and skinny. That's not what actually it is. right? So it looks as if you put a sheet of paper on top of the Earth, and then whatever that sheet of paper sees, that's what the projection is going to look like. This has been used by airline pilots mostly, okay? Because it shows the shortest route between point A to point B, okay? The problem is the directions and distances are distorted. So again, while you are thinking about it, a lot of us have that, and you guys are going to start driving soon, maybe. You guys are almost at that age where you can get your permit, or if you don't already have it. But on your phone, you may have this app called Waze. And what Waze does is it predicts how long it should take you to get from your house to school, let's just say, right? And you can plug in where the shortest distance, or to avoid traffic or construction, whatever. And the reason that it has all of that is because when you're doing this, you want to find the shortest distance, but you also don't want to have to worry about figuring out how long it's going to be till you get there. So by using Waze, it will avoid traffic and everything else, right? The mnemonic projections are harder because you can't necessarily look at this and say, okay, I'm definitely going in this direction, but how long is it going to take me to get there? It's slightly distorted for that reason, because again, it's basically creating a flat map where we know that the Earth is not flat. Okay? The third one is a polyconic one. Okay? Polyconic projections are probably the best ones because you put literally, conic sounds like cone, right? So it's, you are putting a cone over the globe and are able to see clearly that the United States, how wide it is. It also shows you those latitude and longitude lines, but that they are curved, which is what they truly are. Even though there's not actually lines on, you know, the Earth, they are slightly curved. So you have to keep that in mind when you are looking at a map, that where is the latitude line? Where is the longitude line? Especially in this class, guys, when we're going to be talking about time zones and stuff, you kind of need to know that. Okay? This particular map is good for making what's known as a topographic map. After I'm done with all of this, okay, and I teach you this topic, we will be making topographic maps. What a topographic map is that it tells me about the topography. Makes sense, right? Topography, or like what's going on. Is there a mountain over here? Is there a river? Which way does the river actually go? How high up does that mountain go? You know, that kind of stuff. So a topographic map is going to be a very specific map to tell you exactly what's happening at all times. So if you want to know where you should or should not hike, that's the kind of map you want, because if you want to know if that edge of the mountain is steep and you're going to fall to your death, or is it nice and gradual, so you should be okay. Okay? Any questions so far? Okay. What is the best map of the Earth's surface, guys? What should be used out of all of these maps, or any maps that you know about?
A globe?
Absolutely. Right? In this picture here, right, you can see that the Earth's axis is tilted, right, in this globe. Its Earth's axis is tilted. You can actually see the distances. It's not drawn to scale. You know, you have to actually scale it out to see how far things are from point A to point B, okay? If I was to ask you to go in your house and find the best version, right? I have a mini basketball here, but if I was to ask you, the best one, they say actually is a ping pong ball, and there's a little bit of a reason why. Okay, now the shape of the Earth, we've been saying this whole time, is round. However, the true shape of the Earth is not perfectly circular. Make sure you know that the true shape of the Earth is not perfectly circular. Okay. The true shape of the Earth is what's known as an oblate spheroid. So spheroid means sphere, oblate means slightly off and slightly bulging. I'm going to show you what that means. Okay, so it's an oblate spheroid. Okay, so you guys can all see me?
Yes.
Okay, you see my little basketball? It pays to have small children in the house when you're doing science demonstrations. Okay,
Yeah.
so this looks perfectly round, right? What an oblate spheroid would be, I'm trying to block the light behind me too at the same time. What an oblate spheroid would be is if you just go like this. That's it. But it still looks round, right? Did we change the fact that it's round?
No.
No.
No, we didn't, right? All we did is we slightly flattened it at the poles. So to the naked eye, the Earth still looks round. So in all the pictures, in all of the images that we have, in any of the Regents questions I give you, if they ever show you a bunch of pictures, okay, and they say which of the following most accurately depicts the shape of the Earth, and this is a hint, hint, wink, wink, pay attention, okay, you're always going to pick the drawing that looks perfectly circular, okay? Usually on those questions, they'll give you one that looks perfectly like this, then there's another that looks like this, right, and then the other is like an egg, and sometimes they put like a heart on there, completely crazy, but they do. You pick the one that looks perfectly circular because to the naked eye, the Earth looks perfectly circular, okay? So an oblate spheroid just means that you have slightly flattened at the poles. And this is caused by the fact that we rotate. We keep rotating. I can't do this with a tiny basketball. I can do it with the other one, right? But as we rotate, it's kind of like being on, have you ever been on a gravitron before? Do you guys know what a gravitron is?
Yes.
Right? So
Yeah.
if you've ever been to a fair and it's that alien ship looking thing and you walk in and they say stand by the walls and then they start spinning and spinning and spinning and all of a sudden you get like thrown up against the wall by magic and you can lift your feet up and you're stuck against the wall, okay? That's pretty much why the Earth has slightly flattened at the poles, okay? Because it's actually pulling in the center because we're rotating. So when I slightly flatten this, the air inside still needed to go somewhere. So I call an oblate spheroid kind of like it's going to be this basketball or a tangerine, or the only thing I had in my house was a apple. You see how it's slightly flattened up here, but then on the sides, it's a little bit rounder, okay? So, right, to prove that we're actually an oblate spheroid, okay, the diameter at the equator, so right down the middle of the Earth, if you're standing in one place on the equator and you go all the way around the Earth to the other side of the equator, is about 12,757 kilometers. But if I go from one pole down to the other and back around, okay, or the polar diameter is 12,714 kilometers. So you're only off by 43 kilometers, which in the grand scheme of things is not a lot. Okay, so this is all caused by the fact that we rotate. So it's obvious that we're not staying in place, okay, that we are round, and that we're thicker at the diameter than we are from top to bottom and back around. So when you want to think about this, think of Santa Claus, right? Because his stomach is bigger, right, all the way around. His diameter is bigger all the way around. Okay? You guys with me so far?
Yes.
Okay.
Yeah.
Yeah.
Perfect. So looking at this picture here, the darker line, the thicker, darker line is what the Earth actually looks like. Okay. The thinner line is a perfect circle. So it's not crazy to say, oh, by the looks of things, it looks like a perfect circle because it's not that far around, that far off, right? So here we have those pictures that I was telling you about. If this is 1, 2, 3, which one should you pick?
1.
One.
Absolutely. Number 1 is the answer because it looks like a perfect circle. Plus, with 2 here, it's being squished at the equator, which you know isn't true. Otherwise, when you're standing in New York, you could see the tip of South America, which you can't, right? You have to go all the way around, right? And in this case, in number 3, it almost looks like you have squished it down into a hamburger. That is not an oblate spheroid. It is a slight flattening. So to the naked eye, it looks perfectly round. So be very, 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 very careful about that, guys. All right, so for those of you who still are not convinced that the Earth is round, let's prove it, right? We learned when we were doing the scientific method and everything else that you can't just throw out a statement and expect everyone to believe it. You need to prove it by gathering evidence, all right? There are 4 types of evidence that you need to know and be able to explain it, okay? So the 4 pieces of evidence are as follows. Number 1, boats as they move over the horizon, okay? Now, if you're standing at the beach or pretty much anywhere near a body of water where you can actually see a coloring distinguishing difference, right? If you look all the way out, you're going to see the sky meet the ocean, and that looks like there's that separation, that interface, right? It looks like there's that. Yes.
What is this number 1 for? Like, what was the heading?
The evidence on how we're going to prove that the Earth is round.
All right, thank you.
You're welcome. So that interface, right, is the horizon. Horizon is the flat horizontal line, okay? Now, if a boat starts to go out towards the horizon, from your perspective, it almost looks like the boat is disappearing or sinking, but it's not. It's just because of your perspective. So boats appear to sink, quote unquote, as they move away from the observer, which is you, right? Like in this picture, if you are standing at the lighthouse, you can only see straight forward, right? From your perspective. You can't see around the curve, right? It's when you're driving too. It'll say, if you go around the curve, you don't know people are stopped over there at that stoplight, especially the ones over by school, guys. If you're on Horace Harding, right, and you cross over Francis Lewis, right, you can't see around that curve, and there's a light at the end of that block, right, where the school is. So you need to be careful, I guess, if you're going towards from prep to the bus stop across the street, right, there's a curve around there you can't see, and sometimes people go flying around that curve to only find out that there's a bunch of people stopped at the stoplight, and that's how you get into an accident, and that's a problem. Same thing happens here. You cannot see over the hump of the Earth, right? You can't see past that horizon. So in this picture, this first one is the one you would see them actually going over the horizon. You see a majority of the boat. In the second picture here, you only see the smokestack. So it almost looks like it's slowly going over the edge and will sink, okay? If you are a part of the Flat Earth Society, they are actually having a gathering on a cruise ship to prove that this is a lie, okay? If you would like to join them, have fun. Okay. I don't know how they're going to prove it, but they're trying to find the end of the Earth. Okay. But this is the first way that you can actually use your now science knowledge to say, no, you guys are wrong. Here's why. Here's rule number 1. Right. So as they go over the horizon here, it looks like they're sinking, but they're really not. Right. But from your perspective, it looks like they are. Okay. The second type is eclipses. Eclipses. So we have a lunar eclipse and we have a solar eclipse. Either way, okay, you guys listening? Right? Either way, if we have our, let me get something here, our big mamma jamma, the sun, right? If the Earth gets in between the sun and the moon, we're going to have a lunar eclipse. If the Earth gets in between the sun and the moon, we have a lunar eclipse. If the moon gets in between the sun and the Earth, you have a solar eclipse. Okay? Just a little side note. So in this case, right, to prove that the Earth is round, you're going to have the Earth in between the sun and the moon. Why? Because you want the shadow from the sun, the shadow from the Earth to be projected on the moon. The only reason why the moon lights up, quote unquote, and we have phases is because the sun will actually shine its rays towards the moon, and then how we perceive it. The moon never disappears. Even though there's a new moon, quote unquote, the moon never will disappear. It's just that the light from the sun is not hitting the moon at such an angle where we can see it on Earth. Okay? So the eclipse, right, especially during a lunar eclipse, the shadow of the Earth appears to be circular. Right? This picture isn't as good as this one. This is kind of just showing you, right? So here's the moon as it goes from right to left. It goes in front of the Earth, okay? And as it passes in the shadow of the Earth, okay, we see a rounded shadow, right? This is not a straight line. If this was a straight line, it would look like it cuts it completely in half, right? It would look like the shadow is cutting the moon completely in half, but it's not. It's actually a rounded version. Now, this is probably from the 70s, so it's not as good of a picture. Then something like, my favorite is this picture right here, right? You see how it's slightly curved? You guys see that? Right? If you put your finger on the screen, your finger has to curve downward, right? If you're tracing the shadow itself, your finger actually has to go downward, right? It's showing that there is a curve. Okay? All right. The third one is gravity. You guys know how in religion class, Jesus is the answer, right? They tell you in religion, Jesus is the answer. And I say it in religion because in science, he's not. But it's okay. He is to each person. In earth science, gravity is the answer. But you will see the word gravity the entire school year. You will have gravity as the answer majority of the time. Okay, so why is gravity the answer here? Well, the closer you get to the center of the Earth, the stronger the gravitational pull. Okay? Right? So as you go towards the center of the Earth, you're going to have more and more of a gravitational pull. Okay? The fact that the force of gravity changes as you go around the Earth tells you that it's round. Okay? So, what does gravity actually depend on? It depends on the mass of the objects and the distance between the two objects. So, if they are further apart, there's less of a gravitational pull. If they are closer together, there's more of a gravitational pull. If they are smaller objects, there's less. If they are bigger objects, there's more. Okay, so the force of gravity depends on the mass and the distance between two objects. And if you think about it, it should make sense. The planets that are closer to the sun, right, move faster as they revolve around it, right? It's also because they have a smaller distance between the two. Okay, but it all comes down to gravity, right? Think of gravity as a force of attraction between two things. May not be the true definition, but it's easier for you guys to understand that. You guys good? Can I move on?
Yeah. Yes.
Okay.
Wait.
Okay. That's why I ask. Just let me know when you're done, okay? Okay. So, right? Weight is actually a measure of how strong the gravitational pull is. Later on in the year, we are going to, not really that much further, maybe in the next couple cycles, we are going to do a weight on other planets lab where you guys are actually going to calculate your weight based on the gravitational force of the other planets. It's kind of cool. Okay, if you ever go to the Museum of Natural History, usually when you go on field trips and you pull outside and you walk in, it's that big white room and there's scales on the floor. If you jump on any of those scales, maybe one's from Jupiter, maybe one's from the moon, maybe one's from a star, right? It'll tell you your weight, okay? Your weight is gravity dependent. So how strong the gravitational pull is will change your weight, okay? The calculation that you are going to use in order to find weight is W equals, capital W equals M times G, okay? What that is the formula for weight, okay? Where gravity on Earth is 9.81 meters per second squared, okay?
I can't see it.
It's okay. I'm just telling you how it is. Capital W equals little m times little g. Okay, that's the actual formula. All right, because your mass isn't going to change as you move from different places, but the amount of gravity that's pulling you down will. Right? So, when you were looking at this, okay, if you were standing at the equator, you are further away from the center of the Earth. If you are further away from the center of the Earth, it means that the gravitational pull is less. It's less. So therefore, you will weigh less at the equator. When you're at the poles, right, because we are an oblate spheroid, right, and it's a little flattened, the distance between, let's say, the North Pole and the center of the Earth is less than the distance between the edge of the equator to the center of the Earth, and therefore you're going to weigh more. So the more the gravitational pull, right, the closer you are to the center of the Earth, the more the gravitational pull, the more you're going to weigh. Right? That even goes for if you're standing at the bottom of a mountain or the top of the mountain. When you're at the top of the mountain, you're further away from the center of the Earth and therefore will weigh much less. Well, when we say much less, it could be just a couple of pounds. But sometimes a couple of pounds can keep you from being able to wrestle if that's your thing or not. You have to be in a weight class in order to wrestle. So who knows? Okay. So here's just a little summary of it, right? At the equator, you're going to weigh less. At the poles, you're going to weigh more, right? Because we didn't change anything. Like if you look at this picture, the guy who's standing there is in the exact same position. He's looking through the little whatever that is, and everything is exactly the same. The only did was change the location. Either he was at the poles or at the equator. So the further away you are, right, the less you weigh. The fourth one is the pictures, the satellite images, everything like that from outer space. This is the most definitive proof that the Earth is not flat. Okay? You can see the rounded edges, right? You're using those 5 senses of yours, right? You can see them. You could also see that this is probably a hurricane right here, or a tropical storm. Right, you see how it's spinning and there's an eye in the middle, right? And it looks like there was a storm here. So can't really see when this was taken. It looks like it says September or something. So that would make sense because you're in the middle of hurricane season, right? So this is the best evidence to prove Earth's shape. Now, see it from the other perspective, flat earthers say these are doctored photos, that it's not true, so on and so forth. Okay, but this basically proves completely that the Earth is round. All right, so this is your number one evidence. So those are the 4 different types to prove that the Earth is round. You must memorize them. Okay, because you will be asked what is the best piece of evidence, and you're going to have to say one of these 4 specifically. If those 4 are the answers or are part of your multiple choice, the best one out of the 4 are photographs. You guys all downloaded the Night Sky app, right? Remember I asked you to do that? Do you guys remember? I know it was a while ago. The Night Sky app is that little purple one. I don't know if you can see it. Okay. But if you go onto it, there's a lot of little blue, I don't know if it's on this one here. To my left, there's a lot of little blue dots. I don't know if you can really see them or not, but those blue dots actually represent all the different satellites that are in our area in outer space. We are constantly being surrounded by satellites because otherwise you would have no cell coverage. You wouldn't, that's how they predict the weather, because they can see these weather patterns are building up, so on and so forth. So if you want to play around with that app, it's not a bad idea. So here are the 4, right? Just to summarize it a little bit, here are the 4 different ways to prove that the Earth was round. Ships appear to sink slowly or gradually below the horizon. If they were just, if this was true and the ship was going off the horizon, they would just fall, right? If they were, since they are going up and then over and it looks like they're slowly sinking, right? That shows me that curved pattern, right? The lunar eclipses, that's when the Earth gets in between the sun and the moon, right? Earth's shadow shows that it's slightly curved, right, as it gets in front of the moon, right? The difference in gravitational pull, so you're going to weigh less at the equator because it's further away from the center of the Earth compared to at the poles where you're slightly closer, right? And your satellite images, or when the astronauts went up into space and they take pictures of the Earth just to prove that the Earth is actually round. Okay? Anybody have any questions?
Miss G,
Yes.
when will the next quiz be? Is it
I
tomorrow?
can't give you one tomorrow, but I'm going to give you, just plan on the next quiz being next Friday.
Okay.
Next Thursday, because I think next Friday we have off.
Oh,
Whatever
okay.
the end of next week is. Don't worry about this week. This week is a done deal. No tests or quizzes this week. Just worry about next week.
Okay,
What
thank
will
you.
it be on? Miss Gonzalez?
Yes. Well, let me just stop the recording and I can talk to you guys. Okay.